Now, in the previous part of this lecture, we discussed about the standard normal distribution curve and that how to calculate or how to get the areas beneath the curve. Now, if we remember, the standard normal distribution have a mu of 0 and a standard deviation of a population standard deviation of 1. So the z, again, the z values are the areas in the horizontal line, so our x-axis areas. However, in practical applications, when we actually in reality, we rarely have any experiment that actually have a standard or a mean value of these, for example, samples. The mean value that we get from our the sample average that we get from our samples from analysis is not really zero, but rather it actually takes any form of value. So these are non-zero values. So how do we actually apply the standard normal distribution to practical applications where the mu is not zero, and the standard deviation is also not equal to 1? So this is how to convert our sample value. So when we do an actual testing with a continuous variable as the outcome. So this is how do we apply the standard normal distribution to this one. Is first we need to convert the x to the value of z. So for example, a certain sample in for example, a trial in say titration trial. So when you titrate, so we get the value of the amount of aliquot, for instance. So that's the value x. So x is equal to 1.5 ml. So what then? How will we say that the value of x is in which part of the curve? Is it close to the mean or is it not close to the mean? So basically, those are some questions that we know. Is it actually correct? Is 1.5 in practical applications when we titrate, for instance? Is 1.5 a correct value when we titrate? It's actually, is that a correct, or is it an outlier, or is it a representative part of the mean, for instance? So how will we know them? So we need to know how close is it to the mean value. And now, what is the mean value? It cannot be 0 because the 0 is again for the standard normal distribution. So the average value, or the actual or the average value of the say acetic acid concentration on the thing that we are titrating is a non-zero value. So how close is our trial to the actual value? So we need to first convert it, because our standard normal distribution has a mean of 0 and a standard deviation 1. We convert it, basically ilapat ang ating data with the standard normal distribution curve. So here is the equation for converting. If we know the x value, we have a certain outcome of the experiment, value of x. So what is the position of x in the standard normal distribution? So the position z is basically, again, z is the number on the number line at the horizontal number line here. So what is the position of x here? So we just plug it in, knowing the mean. The mean here does not pertain to the 0 value and the standard deviation of 1, but rather the mean here is the population mean of your sample, or even sample means. And actually, ideally, it's supposed to be the population mean. If it's a sample mean, it becomes a t-value. But anyway, this is a population mean and the standard deviation of your outcomes. So let's look at an example. So let x be a continuous random variable that has a normal distribution with a mean of 50 and a standard deviation of 10. So again, why is the mean non-zero? Because this is the mean for the experiment that you are doing. So the mean value in the experiment is 50 and the standard deviation is 10. And we want to know if this is if the standard normal deviation is represents the population, the experiment, or follows, or rather the experiment follows a standard normal distribution curve. So what is the z value, z equivalent of your sample, which is x? So if x is 55, what is its z value? So which position is it on the curve? So basically, we just need to apply this formula. x minus mu all over the standard deviation to get your z value. So applying the formula, you get a z value of 0.5. So the question here is probability to the left of these points. So x of 55, probability to the left of x is 55. And when we look, pag nilapat siya, technically, when we superimpose our distribution to the normal distribution, the 0.5 value is around here. So basically, what is going on here, in order to use the standard normal distribution, apply the principles of the standard normal distribution in our experiment, in the normal day-to-day experimental values, basically you superimpose them. Because if the experiment outcomes of the experiment follows the standard normal distribution, the mu of our experiment is 50 and the standard deviation is 10. So we just superimpose this the bell curve of our experiment to the standard normal distribution. So you just put it at the mu of 0 for the bell curve is now, the mu is 50. So you just basically superimpose it, or ilapat mo lang siya, itapat mo lang siya. Basically that's that. And then you have your value of x. So you are looking for the value x to the left of 55. So basically, if we are just going to use mu is equal to 0.5 and the value of x is 55, in order to get the shaded region, because this one extends to infinity, that's why we have this standard normal distribution, because it's the areas beneath the curve has already been calculated and it's actually in the table. So we no longer need to actually calculate this one manually. So we just need to convert x, if 0 is the 50, then x is 55 becomes 0.5. And then from the table, we can just get the area from 0.5 to the left. So anyway, that's the reason why we have to do, or the standard normal distribution is there, and we just actually convert it so that we can easily know the area beneath the curve, because otherwise we need to calculate this whole one. And remember, this is an asymptotic, it extends to infinity. So good luck on calculating that. So you have this table for normal distribution. That means the mathematicians, statisticians before had already done the calculations for you. You just need to apply it by converting your data, mu is 50 and x is 55 with the standard deviation of 10, to the data they set the standard normal distribution of mu is equal to 0 and standard deviation is 1. So that's how you actually convert it. Just apply this formula. Okay, so let's have another example. So let x be a continuous random variable that's normally distributed with a mean of 25 and a standard deviation of 4. So what's the area between 25 and 32? So what's the probability? For example, if you have a continuous random variable, the mean is 25 and 4 of these outcomes. What is the probability of getting a value between 25 and 32? So again, these values of x, we need to convert it to z. So again, apply the formula and get the z. So now your z becomes, this is 0 and 1.75. So the z value for x is 0, z value for 32 is 1.75. So it's between 0 and 1.75. And applying what we have learned in the previous video lecture, previous part of this lecture, in the preceding video, we just get the area between 0 and 1.75 on the z curve, the standard normal distribution curve, and this is your answer. So here is your standard normal. Here is the standard normal distribution axis. So 0 and 1.75. But in your problem, it's for a random variable between 32 and 25. So you just converted your the values, your x values, to become z values by applying your formula. X minus mu over standard deviation. So let's have a more concrete example for, rather than simple example. So we have here some applications. So here. So the average student loan debt was $37,172 per borrower in 2019. So suppose that the 2019 student loan debt for all borrowers are approximately normally distributed. So when we say approximately normally distributed, the values, the outcomes of the probabilities of all outcomes follows or can be approximated very, very, all very similar to a bell-shaped standard normal distribution curve. So the mean of the student loan debt is a value of 37,152. So that's the average loan debt of the 2019 students, of the students in 2019, and the standard deviation is 5,230. So what's the probability that the 2019 student loan debt of a randomly selected borrower? So if we look at those people with debts and we just get one. So what's the probability of getting a value between 30,216 to 39,996? So what's the probability of getting when we ask a certain students out in the streets and ask for his debt? So what's the probability that his debt is between 30,216 and 39,996? So if we are going to analyze here, so you have here a standard normal distribution, and the average, the mu here is 37,172, and the standard deviation is 52.30. So our x values are 30.216 and 39.996. So we are looking for a value between 30,216 and 39,996. So areas beneath the curve, because it's a probability. Probabilities are areas beneath the curve. So areas beneath the curve between these values. So first convert our x values. So apply the formula, and this is the z. We need to apply this formula in order to get the points in the terms of z, so that we can look this up in the table. So according to the table, the z value for 1.33, or rather, the z value for 30,216 is negative 1.33, and the other one is 0.54. So the shaded area between the curve is between negative 1.33 and 0.54. So here is your shaded area between negative 1.33 and 0.54. So this, if you look at this one, is it just me, or is it a bit skewed? No, it's just me, because the shaded region is a bit skewed to the area is around to the left side. Anyway, so you approximate, since the statement of the problem said that, explicitly state that it approximates normal distribution, so we are going to apply the normal distribution. So this is the mu, and the standard deviation is not shown. Anyway, so this is negative 1.33, area beneath the curve between 1.33 and 0.54. So applying what you have learned in the preceding video, so you just get the area 0.54. So this is a 0.754 minus the area to the left of negative 1.33, because remember, the values in our table tells us the values to the left of the curve. So again, the interval is 0.6136, or that means that 61.36% chance of getting when we ask a random student in the streets and ask for his student debt, his answer, the probability of getting a student with a debt between 30,000 to 39,000 is 61.36%. So basically, that's what this means, and this is the value of the shaded area. So the value, again, the value of the shaded area is a probability. So when you randomly snatch a student out of streets, ask them his debt, 61% chance is it's between 30,216 and 39,996. Let's have another example. The racing car is one of the many toys manufactured by Mack Corporation. The assembly time for this toy follows a normal distribution with a mean of 55 minutes and standard deviation of 4 minutes. So the company closes at 5 p.m. every day. If one worker starts to assemble a racing car at 4 p.m., what's the probability that she will finish the job before the company closes for the day? So you have here, the company closes at 1 p.m. 5 p.m. So it starts at 4 p.m. So you have 1 hour of assembly time. Now, the mean assembly time is 55 minutes and a standard deviation of 4 minutes. So meaning, it's 55 minutes, and then the faster, if a person, when we say standard deviation, it's if it's faster, if you are 1 point faster than the mean, so that means your assembly time is 59 minutes, something like that. So anyway, so our x now is how many, or how many minutes is the 4 p.m. to 5 p.m. 4 p.m. to 5 p.m. is 1 hour or 60 minutes. So if the mean is 55 minutes and the ST is the sigma is 4 minutes, so what's the possibility of finishing early? So you have our x is 60, because again 1 hour is 60 minutes. So just get the z value applying the data, so that's 1.25. So what's the probability of getting that you will finish the job before the company closes? So the probability here is the area beneath the curve from 1.25 to the left. Just simply uh, getting this one, the z here. So the probability of getting a value that is less than 60 minutes. So you need to finish here before 1 hour. So because again, the closing is 5 minutes, so 1 hour. What's the probability of getting, or of the worker finishing it within an hour? So within this value. So the the value is less within an hour, so 60 minutes or less. That means 60 minutes or less. So if z is less than or equal to 1.125, so that's 60 minutes or less. So when we say that, what's the probability of the worker not finishing on time? So that means the value of 60 minutes or greater. So that instead of z is less than or equal to negative 1.25, it becomes z is greater than or equal to 1.25. That is not finishing on time. But here the question is, what's the probability that she will finish on time? So that means finishing on time means getting it within 60 minutes. So within this prescribed time. So less than 60 minutes or less. So less than or equal to 60 minutes. So since 60 is equal to 1.25, based on the the conversion to z of 60 minutes is 1.25. So the probability is less than or equal to 1.25. So this is our probability distribution graph. So less than or equal to, so from the 1.25 up to the left of the graph. So this is your probability. Now, if the question is switched, what's the probability that the worker will not finish on time? So that's 60% or 60 minutes greater. So 60 minutes or greater, so the shaded area becomes those to the right. So it becomes 1, because again, the total area is 1.001 minus 0.894. So that's around 1.11, 1.056, some about. So that's not the probability of not finishing on time is around 10%, and the probability of finishing on time is 89% or 0.8944. So basically that's our probability. So another example, Hopper Corporation produces many types of soft drinks including orange cola. The filling machines are adjusted to pour 12 ounces of soda into each 12-ounce can of orange cola. However, the actual amount of soda poured into each can is not exactly 12 ounces. It varies from can to can. It has been observed that the net amount of soda in such a can has a normal distribution with a mean of 12 ounces and a standard deviation of 0.15 ounces. So, what is the probability that a randomly selected can of orange cola contains 11.97 to 11.99 ounces of soda? So, for this type of question, so again, this is our x, 11.97 to 11.99. So, we just need to convert our x with a mean of 12 and a standard deviation of 0.15. So, this is our x value. So, since it's a question of between 11.97 to 11.99, so it's between these two values. So again, convert it and look at the shaded region. So the probability of getting a cola that has the actual amount of soda between 11.97 ounces to 11.99 ounces is 0.2286 or 22.86%. So basically that's your That's the answer for that. So that's what's the other question. The other question, what percentage of the orange cola cans contains 12.02 to 12.07 ounces of soda? So again, convert these values of x to z. So 12.02 is 1.33 and 12.07 is 1.33. So the getting the shaded region between them is, the shaded region is 0.0918. So the probability is getting is 9.18%. But the actual question is what's the percentage of the cola? Since the probability here is the frequency, relative frequency, that means if you have 100 soda, 9.18% of the time you will get a soda that's between 12.02 and 12.07 ounces. So that means around, if it's a frequency distribution, this is 9.18% of the sodas manufactured is between this one. So that's actually, uh, if you can see, it's quite flexible with the probabilities because it's a frequency probability. That means sampling every, getting the whole population, 9.18% of the population falls under this shaded region. So you have 9.18, and it's also the probability of getting, when you randomly get a soda, you get a soda that's between 12.02 to 12.07 ounces. So this is 9.18% of the time. So that's the thing about frequency distributions and probabilities. So basically, it's actually comparable, or we can approximate 9.18% of the people, or the soda cans, is the same as the probability of getting a soda can within this one. So these are further examples of your calculations. So I want to have a slightly different example. So let's look at this one. Find the value of z such that the area under the standard normal curve is 9 to the left is 0.9521. So here is the question is switched around a bit. Instead of us knowing z and finding the area beneath the curve at number z, we want to know what value of z would give us an area that is 0.9251. So the area should be 92.9251. What's the value of z? That will give us an area of 90.9251. And that is, looking at the table first, what's the value that will give us? 0.9251. That's 1.44. So the value is 1.44. So these are some other examples. So what's the value of getting an area under the standard normal curve in the right tail is 0.050. So this one is in the right, 0.05 in the right side. So the remaining area is 0.995. So since the table gives us the area beneath the curve to the left of the z value, and this is z to the right, so we just get 1 minus 0.005 to get the area to the left, and then look it up in the table. So according to the table, 0.995. So let's look at the table. 0.9. So instead of looking at this headers and the z value in the table, so we're going to look at the actual value. So with each value 0.995, 98990104. Okay, 06. This is 04 and 99. So it's actual value again. 0.9950. So 0.9950. 45, 46, 48, 61, 57, 53. 9949 and 9951. So you have 9950. So it's between 2.50, 9949. This is 7. So 7 and 8. Where is it again? 99599. 0.257 and 0.258. So that is the value. So it's exactly between. So it's around 995, between 9957 9958. So again here, instead of getting the average, just find the one that is closest, and then it's either this one or this value. So either is correct for this value. So again, this is another similar example. So instead of just getting the average, it's much better to just choose one of the two possible outcomes. Okay, so if we extend this problem to our x values, so the normal curve with known values of mu and sigma, that's the mean and the standard population standard deviation, for a given area under the curve to the left of x. So the value of x is equal to, actually this is just the same equation, we just rewrite it to find x. Here, the x is missing. So let's look at an example. So the life of a calculator manufactured by Calculators Corporation has a normal distribution with a mean of 54 months and a standard deviation of 8 months. What should the warranty period be to replace a malfunctioning calculator if the company does not want to replace more than 1% of all the calculators sold? So that means the calculators, or what is because the distribution from the previous examples, let's look at the previous example. Calculator. Okay. Lifespan of calculator has a mean of 54 months and a standard deviation of 8 months. So the guarantee that the calculator starts malfunctioning within 36 months of the purchase and will be replaced by a new one. So that's the guarantee. But the value here is 54 months and 8 months. So they don't want to replace, or rather, of the calculators they manufacture, they only want to replace 1% or less. So that means what should be the warranty period, that such that the majority or 99% of the calculators must still be functioning, or rather, uh, because it's 1% of the time. So how do you, okay, so let's actually look at this example. So okay, so we have here the mean working average time where the calculator is working. So 54, this is the life expectancy, let's say, of the calculator. So 54 months. So the majority of the calculator, so the average time the calculator will malfunction is after 54 months. So that's the life warranty, or lifespan of your calculator is 54 months. Now, since the company, for warranty purposes, the company doesn't want, or they only are capable, or they don't want to replace calculators that that or rather they only want to, they don't want to replace a large amount of calculators. Let's say they can only they only want to replace calculators that malfunctions, among all of them is 1%. So that means the calculators, because again, calculators malfunction, the actual malfunctioning time of calculators is different for each calculator, but they only want to replace 1% of the calculators they produce. So what is the probability of getting a calculator that will malfunction before the warranty time? Should be 1%. So the shaded area here to the left must be 0.01. So that means the calculator should malfunction during or within a certain within the warranty period 1% of the time. So there's only, meaning to say, there's only 1% chance of the calculator malfunctioning during the warranty period. So that's what they are actually looking for. So what should be the number of months that they should set, so that they would only replace 1% of the calculators they manufacture instead of getting all of the calculators manufactured. So that means you want to have the probability as 0.01. So that's the area beneath the curve. So we can already know what is the value that gives us 0.01. We look at our distribution curve, what will give us a value of 0.01. This is 0.001. Okay, I'm just gonna negative 2.33. So 0.02 point. Okay, so here is actually this is the closest. 0.01 is 0.0099. So the closest is negative 2.33. So negative 2.33 this is our z value. So what is now our x value? So this is the number of months. So in our probability distribution, our x is the number of months. The calculator's malfunction. This is the lifespan of the calculator. So we only want to know the percentage of calculators that will malfunction at uh, at a certain value of x, such that only 1% of them, the first 1%, we are basically looking at the first 1% of the calculators they manufacture that dies off or becomes, that malfunctions. So we have negative 2.33. This is the z value that gives us a shaded region 0.01 to the left of the curve. And to get the x counterpart of that, we just apply the equation. So we will get, apply this equation, you will get 35.36, or rather 35. So this is 35 months. So this is, our unit is in months. So the warranty is 35 months. So that means that they should give a warranty of more or 35 months or less from the purchase date. So that basically it's based on the probability distribution, only 1% of the calculators are expected to malfunction after 35 months. And that is how they can only want to replace only 1% of that. So this is, let's look at another value or another example. So again, from the student loan debt. So suppose that the 2019 loan debts for all borrowers are approximately normally distributed. So the same questions as before in our previous example. Now, approximately 10% of all such borrowers are greater than Roger Smith's. So what is Roger Smith's student loan debt? So 10% or greater. So we are looking at the, if it's greater, it's to the right. We're looking at the 10% is the area to the right. So the 10% is 0.10. The area to the right of the curve is 0.10. So we need to find what is the actual value of Roger's student debt. So the value to the right is 0.10. That means since our data gives us the values to the left, we just get 1 minus 0.10. So that's around 0.9. So the area around here is 0.9. 0.9. So what is 0.9? So 0.9 is already around 997,915. I think this one is easy. 912. Is it 1 to 128? 1 to 1.28. 1.28. Okay. So this is 1.28. So that's the value of z. So convert the x. So we just need to calculate or plug it in the equation. So the value of Roger's debt, since 10% of the students are greater than him, the value of his debt is actually about 43.86, $43,866. So that's his value of loan debt. Okay, so that's it for this part of the lecture. So in the next part, we will discuss about normal approximation when we apply it in the binomial distribution table.